First of all, the presentation that we had now, it was very, very interesting because almost all the topic that I'll treat in my presentation now is more or less related to what the presenter said, and in particular, I treat all the arguments, but in other perspective. So. First of all, I present myself. My name is Gianluca, and I work for Engineers. That is a company located in Italy, in the Tuscany. And we work basically with satellite system, developing hardware and software and data handling system for satellite. And as there was written in the last slide, we work on real missions that are the most complex one, both in terms of requirements and reliability. As we heard this morning and now in the afternoon, there are several missions that can benefit of artificial intelligence directly on board, and in particular science and earth observation and explorative and telecommunication missions. And this type of mission can benefit of image analysis, data analysis directly on board, increasing indeed satellite autonomy and obtaining some new features such as autonomous guidance, navigation and control, or improved the FDIR system. And as we saw, there are a lot of applications that already exist and can be implemented directly on satellite. For example, convolutional neural network for object detection, computer vision in general, recurrent neural network for data analysis, satellite autonomy, and stuff like that. More complex applications that exploit, for example, transformers that are very complex to be run directly on a satellite, or object detection and orientation understanding and stuff like that. But in order to execute this type of application directly on board, we need to understand at least what type of hardware are available now. And as we know, the major part of these algorithms is based on a paradigm that is called single instruction multiple data. This means that the same instruction is spread on all the cores, all the processing element of the system, working on different data, and these increase, as you surely know, the final throughput. And the hardware that is able to do that are GPUs that, as we will see, are the most appropriate thanks to their architecture, and dedicated hardware accelerator, and finally FPGAs. GPUs were invented to deal with graphic problems, and in particular with to work with computer imaging and computer vision algorithm at the beginning. But then we understood that it is possible to spread several type of instruction and several instruction on different cores, obtaining an incredible speed up. And artificial intelligence perfectly apply to this situation. GPUs have pros and cons, indeed. The first pros is that GPU have very big memories, very high memories and frequencies. The cons is that if you consider this type of accelerator for space application, the robustness of the internal architecture is low, because this algorithm is thought for commercial market, and they don't have any type of resistance of ruggedization that is usually required to work in the harsh space domain. The evolution of the GPU then were the dedicated hardware accelerators. These type of accelerators are, in a certain way, the evolution or the miniaturization of the GPUs, and they were born as part of the edge movement that a couple of years ago started in order to move the application from the cloud directly to the edge in order to improve the privacy issues, to reduce the data movement and stuff like that. There exist several type of hardware that have been proposed in this sense, and in particular we can remember for sure the Movidius stick, the neural computing stick that was adopted in FISAT 1 and FISAT 2, the mission demonstrator, the ESA missions. And the Jetson family that we for sure saw in several papers regarding space domain and space application. And one less lucky hardware that is the tensor the tensor board from Google, the TPU, the tensor processing unit, that this hardware was less used since it is strongly linked with the data type that have been created by Google itself, that is the tensor. Finally, we have the FPGAs that are very robust, and as all of us knows, there are several of these hardware that are space qualified and can resist to several kilorads of radiation. And the problem of these hardwares is the lack of automatic tool that allows to implement stuff on them. And in particular, there are some solutions that are available, for example, VTCI or vector blocks, but these are limited to some type of layers, and the performances is not what we usually expect, and also create a sort of customization in the network could be quite complex sometimes. For this reason, engineers, more or less 5 years ago, started with the development of a new FPGA IP core that unify of the characteristic that we saw before. So the capability of a GPU, the capability of parallelization, the capacity of parallelization, and the ruggedization typical of FPGA system, but inside a very low power design. This is a fully space qualified and flexible solution that allows to run not only artificial intelligence, like for example VTCI or vector blocks, but it is possible also to run and accelerate computer vision and APC applications. The GPU is composed. Sorry? Okay. The GPU is composed by 8 different compute units. These compute units can be increased in some type of architecture, but generally we try to use only the energy or the computational power that is needed in a typical mission, and all of these compute units can work from 4 to 32 bit per operation. So this means that you can create different type of quantization that are usually required in all type of FPGA or embedded application or platform, and reducing as much as possible the loss with respect to the original model. The entire architecture has been thought taking in mind the single instruction, multiple data paradigms, and so there is memory architecture that enhance throughput and efficiency, and you can see here from the block that is called the global memory controller, and this memory controller is directly connected with the CU that are composed inside that are composed by 8 processing elements inside. This number of processing elements can be customized, but the typical number that we used in other missions is 8, that maintains a good trade-off between the performance and power consumption. In addition to the GPU that I present, the need of a processor, so a CPU or an external controller that should in a certain way be the head of the GPUs or the external accelerator is one of the biggest block for the adoption of AI in a real mission. And for this reason, we implemented this GPU headset controller that is a system that allows to run all the artificial intelligence algorithms directly on a FPGA only board without the necessity of an external processor. Indeed, if you have an external processor, an OBC, an ICU, or another type of intelligence controller, you can send command and receive telecommand from the GPU, but it is only let me say, nice to have feature, and it is not completely necessary. This controller has been designed together with the request of some customers that wanted a dedicated board where you can run your application, and as we listened this morning, there are these applications are not fully reliable on space because they usually are run on hardware that is not completely reliable, and this was used to limit the interference that this GPU can cause to the entire system. The GPU has its own framework that accept 3 different type of high-level framework, starting from TensorFlow, PyTorch, and ONNX, that are the most famous frameworks for AI development. And in addition, in order to support also computer vision application, we are able to design more or less all type of kernel that support OpenCL 1.2. Together with the engineers GPU headset framework, the combination of the input from the high-level framework and the OpenCL kernels create the so-called application. However, also in this case, the software guys in this case were not happy of this solution because it required some hardware skill, and we also developed the GPU headset dev kit, that is a system that integrates the GPU headset directly on AMD Xilinx ZCU 104, controlled by the CPU. In this case, an external user can interact directly with the GPU by Ethernet, and exploiting the framework that we saw at the beginning, and this is better shown here. It is possible to prepare your AI model, convert it in through the OpenCL library and the compiler, the dedicated compiler, quantize all the weights inside the model that you are trying to porting, obtaining the final schedule and the final scheduler of the layers. And if you need some pre-processing or post-processing, you just need to add the potential layers that are not supported or additional layer that are considered custom option. And this simplify as much. This is the solution that we found to simplify as much as possible the implementation of complex AI system directly on board a real satellite. Thank you.
Thank you for the talk. So questions? Yeah, go ahead.
Yeah. How is when you run a network model? How do you mitigate the memory fetches? So does the GPU at SAT have an internal cache?
Yeah. Yes. So let me go back here. Inside the global memory controller, there are some HIDAC system that maintain the coherence with the cache itself, and there are also some caches that speed up the data reading and writing directly from the CUs.
Mm-hmm. And I guess intermediate feature maps get stored on chip memory.
Yeah. There is also exactly. Each CU is a little bit more complex than what you are seeing now. There are 32 registers inside each compute unit. These registers are configurable, so you can extend it or you can exploit a shared memory between all the CUs. For example, if you want to maintain convolutional kernels that are common to all the operation, and this is stored directly inside the VRAM of the FPGA, indeed protected by an HIDAC system that avoid data corruption during the operation in space.
And one last question: what kind of neural networks do you run?
We implemented several type of neural networks, convolutional, LSTM, GRU. I just talking about the main layers, then the standard one, for example, MobileNet, SqueezeNet, stuff like that. But yes, one example with the transformer, some FDIR application for ESA projects. Yeah.
Thank you.
You're welcome. Indeed, the performance cannot be truly compared with a commercial GPU. But in this case, is absolutely the case that were discussed in the presentation before, because here we want to have only the power, the computational power that is really need for run the application, with the time, the execution time of the cycle of the execution that we maintain as minimum as possible, but without exploiting some hardware that is an overkill for the satellite itself.
Yeah, hi Gianluca, thanks for your talk. I just have a question. Since I understand that you have a bit more flexibility towards various algorithms than what we have already tested during ASAP with feasibility studies with the KTH, perhaps we could discuss or already might have an idea if you would you could try a very small variant of YOLO, the only look once computer vision object detection algorithm, and see if it's feasible to have it in such setting, and what's going to be the requirements to if it's not possible, how we could make it possible, you know. Perhaps we can discuss a bit afterwards after my presentation that you might get some more details, because it's interesting that you have the flexibility to have LSTMs, also some attention models.
Yeah. Perfect. Well, we already ran successfully a tiny YOLO, but yeah, as you know, is smaller than the YOLO V6 or V5. But yes, we can discuss about it.
Yeah, perfect. Thank you.
Thank you too.
Okay, questions maybe from the chat.
Any questions from online participants? You can just unmute yourself and ask.
Yeah. Seems like everything was clear. I speak the speaker again.
We're very puzzling.